Hello. So, as I mentioned in the last lecture, we have discussed finite difference approximations for hyperbolic PDEs. So, now let us discuss method of characteristics. So, this is a very special method. This is a kind of numerical treatment based on analytical approach, because for hyperbolic PDEs generally we talk about characteristics and then capture the solution via characteristics. So, now similar technique we are using it, however, we develop a numerical scheme. So, before we proceed we must understand what is the characteristic curves. So, of course, many of you when you have attempted your first course on PDE, the analytical one. So, you would have solved using separation of variables, and there you would have talked about this is the characteristic equation and these are the characteristic curves, etc. Okay. So, let us review what is a characteristic curve first, and then slowly we understand. Okay. So, method of characteristics for hyperbolic PDEs. Okay. So, when I say this, first we have to understand what is a characteristic. Okay. So, typically let us start with just a review on first order, then we discuss second order. Okay. So, review is it would be better to consider a physical example. So, convection of a fluid particle. Okay. So, say we want to discuss in 1 dimensions. Okay. So, the corresponding equation is equals to 0. So, where f is any fluid property. Okay. So, this is local rate and this is material rate. So, that means any fluid property, this is a local change with respect to the time, and this is how it percolates with respect to space. Okay. So, you can see, so this is the velocity which is driving the material changes. Okay. So, now in this case x t, which will be location, is related to u velocity by dx by dt equals to u. Okay. So, now one can integrate this and obtain so u one can obtain, which is path line. Okay. So, here in x t space, so we have, so these are the lines and this is the path line. Okay. So, now along the path line dou f by dou t u dou f by dou x equals to, along the path line okay. So, this is d f by dt and we have this equals to 0. So, that means f can be obtained as constant. So, that means the fluid property has been convected. The inference is fluid property has been convected. So, we make use of these, and in this case this path line is called characteristic curve. Okay. So, what do you mean by a characteristic curve? So, these are characteristic curves or say n dimensional n minus 1 dimensional surfaces, because in n dimensional surfaces with a special feature. Okay. So, this is a typical definition. When I say surfaces, these are hypersurfaces. So, those who do not know, you need not worry, it is like more than 3 dimensions kind of x, y, z and t. So, that means if you have 2 dimensions, the characteristic curves are 1 dimensional. If it is 3 dimensions, the characteristic curves are 2 dimensions, okay, with a special property. What is the special property? You can see along which the data gets convected, the data gets percolated. Okay. So, that means in a one dimensional case, in a such a simple physical example, one can see any fluid property f has been convected. Okay. So, along a path line, and hence this path line is very special for us, and this is called a characteristic line. Now, similar concept, if we would like to extend it to our second order. Okay. So, then we have what is the scenario there? We have higher order derivatives, right, because you have u x x, u x y, u y x, etcetera. So, now when information percolates along these lines, then for example, if there are some discontinuities, let us say places where initially you do not have derivatives, derivative does not exist initially, and the same information gets percolated, okay, along those. So, this is what we are trying to do in the method of characteristics is find out such lines and try to compute the solution along those lines. So, this is a typical thumb rule kind of. Okay. So, now let us see for second order how the characteristics come into picture. Okay. So, we consider second order okay. So, where A, B, C, E all of them are functions of x, t, u, u x, u t. Okay. So, I did not write each one of them, but they are. So, now what is aim? Aim is, as I mentioned, can we simplify partial derivatives so that the given equation star can be integrated easily. So, this is relative. What do you mean by easily, one may ask? In some sense, by converting into the curves, that means by reducing the dimension in this case. Okay. So, the answer for this is yes, of course. So, that is the aim. So, how do we do it? So, this is a typical u x equal to p, u t equals to q, and u x x is alpha, u x t is beta, u t t is gamma. Okay. We introduce, then let C be a curve on x t plane on which we know the values of u, p, q via du equals to dou u by dou x, which is equals to p dx plus q dt. So, call this 1. So, let C be a curve. Okay. So, this is x, this is t. So, this is any curve on which we know u, p and q via this relation. So, this is a in analogy to the one dimensional case. Okay. So, on this curve, let us say we know via this relation, right. So, here where dt by dx is the slope of tangent to C at x t. Okay. So, what is our aim? So, we know on C u, p and q are related via q dt, which is 1. Then the question is it possible to find values for alpha, beta, gamma on C such that A alpha plus B beta plus C gamma plus E equals to 0. What is this? This is our original equation. See, this is our original equation which we have considered, A u x x plus B u x t plus C u t t is 0, and this is the notation we have adopted. Okay. So, then if u, p and q are known, we would like to determine on C these alpha, beta, gamma such that this is satisfied. Okay. So, that is what the question, and the answer to this is yes. Okay. Of course, via C we do this. Okay. So, let us see how we do. Now, on this curve dp is, since p is known on this curve, it satisfies this, which is now p x is u x is p. So, p x is u x x. Okay. Then this is u x t, because this is p is u x and p t is u x t dt, and this is alpha dx plus beta dt, call it 2, then dq so this would be u x t dx u t t dt. So, this is equals to beta dx plus gamma dt. Okay. So, now the answer we want to see whether we can compute the derivatives, okay, double derivatives, because along the characteristics they propagate. So, in order to find out the double derivatives, we go back to the characteristics. So, that is the concept. Okay. So, we have du equals to p dx plus q dt, then we have dp equals to alpha dx plus beta dt, then dq is beta dx plus gamma dt. Okay. So, we have this, then eliminate alpha and gamma from 1 to 3 as follows. So, why are we doing this? We will come to know a little later. So, we want to eliminate alpha and gamma, okay, because alpha beta is common to both. So, alpha and gamma, okay, we want to eliminate. So, to do this, so this is equal to so from these three equations. So, we get this. Okay. So, now let us substitute in the PDE star. Okay. So, that is in this. Okay. So, we substitute. So, remember we are trying to substitute for u x x and u t t. So, there will be definitely u x t remain. So, if we do that, we get u x t So, we get this. So, as I mentioned, we substitute in here. So, when we do that, we get u x x will be replaced, u t t will be replaced, and we collect the coefficients and we get this. Okay. So, now note that A, B, C are independent of alpha, beta, gamma and 4 is independent of alpha and gamma, because we have eliminated them. Okay. So, this can be made independent of, this is nothing but beta. So, this can be made independent of beta if this is 0. Okay. If this is 0, whole thing is independent of beta and this relation is satisfied. Okay. So, four can be made independent of beta, which is u x t, if this is equals to 0, which is a curve on which, see, this is 0, a dp dx dt dx plus c dq dx plus e. Okay. So, what we are trying, so this is also independent of the beta if this is 0. So, that means which is a curve on which. Okay. So, this relation holds. So, this is very important for us. So, now what does it mean? What does it mean? Slope of the tangent at, see, because dt by dx is slope of the tangent. Okay. So, this is c, x and t. So, if you take any point x t, dt by dx is slope of the tangent at x t, right. So, slope of the tangent is root of this equation. Okay. So, that is first inference. So, let us write down. So, let us write down a dt by dx minus dt by dx plus c equals 0 implies slope of the tangent at a point on C is a root of the equation a m square minus b m plus c equals to 0. Of course, m is dt by dx. Okay. So, this is say C, right. Then next inference, along directions tangential to C, from points on C, we have this relation. So, this gives that the slope satisfies this relation, then in that case this relation holds. So, it is a combined. So, slope satisfies this equation, then along directions tangential to C from points on C, we have A dp dx dt dx dq dx E dt dx equals to 0. Okay. So, now we have two roots for this equation, right. So, what will happen in that case? At each point of the solution domain, the two roots give two directions along which there exists relation A dp dx, this dq dx dt dx equals to 0, where there are no derivatives with respect to t. Why we are making this conclusion? Because we forced from here, we force this becomes independent of t if this is 0. Okay. So, hence this is 0. So, this equation satisfied means there are no derivatives with respect to t. Okay. So, now we have to talk about these two roots, right. So, the curves, so we can give some bullets. So, curves whose slope m is given by am squared minus bm plus c equals to 0. These are called characteristic curves. Okay. So, that is where we are relying on the characteristic curves. So, that means what did we do? We have tried to capture the curves along which the derivatives are vanishing, okay, with respect to t, right. So, we have eliminated alpha and gamma before, and then we made it independent of beta, and we have captured the corresponding curves. It has two roots, and then it corresponding to each curve we get each root we get a characteristic curve. Okay. So, now what information these characteristic curves give, and moreover is it true that always we get these characteristic curves. Okay. So, it is a simple question to answer, because we have a quadratic with respect to the slope. So, now definitely it depends on the kind of roots we have, right. So, we have to answer this question based on the roots, that is where the second order classification has been done based on the behavior of the roots. Okay. So, now in this case case 1, say no real characteristics. So, this means b squared minus 4 a c is less than 0, and according to second order classification we call this elliptic. And another case 2 characteristics at every point and they are real distinct roots. This is the case of real distinct roots. So, b squared minus 4 a c greater than 0, and this is the case of hyperbolic. Then single characteristic, and this is the case of, so only one root. So, this is the case of parabolic. Okay. So, which means, for example, if since the information passes through these characteristics, in case of parabolic and hyperbolic, at least there is somebody who can percolate the behavior. So, if the derivatives are discontinuous, then the derivatives are definitely discontinuous along those. But in case of elliptic, since there are no real characteristics, so one cannot rely on the characteristics. So, the entire solution domain will be responsible for computing the next one. Okay. So, in case of elliptic, that is the reason we have a complete closed boundary. Okay. So, we do not have any real characteristics on whom we depend and try to compute the solution. Okay. Whereas, in case of parabolic and hyperbolic, we have somebody on whom we can rely and try to compute the solution. Okay. So, we are talking right now of the hyperbolic. So, let us see how we can rely on the characteristics and compute the solution. Okay. So, solution of hyperbolic equations by method of characteristics. Okay. So, let us, given our second order PDE, so the characteristic roots, the characteristic directions are roots of equals to 0, and along these we have a dp dx So, this is what we just now inferred. Okay. So, now this can be recast in a slightly different way. So, that is a dp dt by dx dq dt is 0. Then since we are discussing hyperbolic, assuming star is hyperbolic, the roots of, so this is C, the roots of C are real distinct. Okay. Let them be, let these roots be dt by dx equals to f and dt by dx equals to g. Suppose if we take, so what is the idea? We would like to make use of these characteristics and solve the value, okay, right, because these characteristics are spread over the entire solution domain. So, now instead of making use of the grid by discretizing the domain, we would like to compute the solution along these characteristics. Okay. So, if we consider any curve gamma which is non characteristic curve, maybe along which the initial, so where initial data is given. Okay. So, this is the gamma. Now, at each point we have two characteristics and we call them f characteristic and g characteristic. So, say this is a point P. Okay. Similarly, at point Q we will have, right. So, if gamma is such a initial curve, so I have written previous non characteristic curve. So, then at P we have f characteristic and g characteristic. Then again at a point Q, so this is f characteristic and g characteristic. Okay. So, what you could see, the f characteristic of P and g characteristic of Q, they are intersecting at R. Okay. And what is this point? R is x r T r. Okay. So, f characteristic at P and g characteristic at Q intersect at R, which is x r T r. So, the idea is we would like to compute the solution at this point. So, then you can see, suppose if you consider another point, then again we will have. Okay. So, now again next point of intersection. So, then higher levels similarly. So, that is how numerically we would like to compute, right. So, the idea is to compute the solution at intersecting points. Now, you can see these are curves. So, how do we compute? So, we treat them as initially to start with, treat them as straight lines, okay, and then interpolate. Okay. So, then we can refine. So, to start with, initial approximation, treat P r and Q r as straight lines with slopes of obviously F p and G q respectively. So, the idea is we would like to make use of this as straight line approximations with the slope F p and this is G q, and interpolate and compute the solution. So, if we do that, then what would happen? dt by dx equals to f. So, this implies, so this is the interpolation, because on the characteristic curve this is true on f characteristic. So, T r minus T p equals F p x r minus x p. So, this p means capital P point. Okay. So, it is this p I am talking. We get another p which is the first derivative later on. So, this is r. Okay. So, now this is approximated, right. Now, along G. So, this implies T r minus T q is G q x r minus x q, right. So, that means we have two equations in two unknowns. What are they? Our first task is to compute the point r. So, when we compute the point r, then we next task is to compute the solution at r. So, this interpolation gives the point r. Okay. So, once we have the point, we get the solution there. Okay. So, how do we do that? So, we have to make use of the relation, the second relation. So, we have a dt by dx dp. So, these are small p's, please do not get confused with the point. So, these are the first derivatives. So, this is a relation which we had f dp, because this is f characteristic I have substituted. And similarly, on G then consider, so we have to give some numbers. Okay. So, E1 implies on, not on, maybe along PR. So, now we are ready to, so this is PQR and we have approximated as straight lines, right. So, now consider this equation along PR, this can be approximated A P at the point P, then F P, then, so this we are considering E1. So, D P. So, D P along P R will be P R minus P P, P R minus P P plus C P, then D Q Q R minus Q P, okay. Then E P D T T R minus T P equals to 0. Okay. Then similarly, maybe I do it, consider E 2. This implies along Q R. So, along Q R, okay, what is E 2? E 2 A G D P plus C D Q E D T equal to 0. So, we would like to approximate this. So, this will be A Q G Q P R minus P Q plus C Q Q R minus Q Q plus E Q T R minus T Q equals to 0. Okay. So, we have two equations in two unknowns for XR TR. This was the earlier scenario, which are these. Okay. So, call this E1, E2. So, we had these two equations in two unknowns, and right now we have obtained another two equations. So, maybe we have to write down further we have A P F P this is one and the other one is this. Okay. So, if so these are so the remark is if XR TR are known, then we get, what do we get? We get P r and Q r using E 3 and E 4. Okay. And hence, U can be obtained at R. Okay. So, once we get a P r and then U at R, can be obtained by du equals P dx plus Q dt. Okay. However, the better approximation is replace P and Q along P r by average. So, that means U r minus U p is okay. So, let me have a quick brief, because this is slightly complicated. So, we have at each point two characteristics. So, then we would like to make use of the characteristics and get the solution. So, before we arrive at the characteristics, then we have important tool on which we are relying is this. Okay. So, these are the characteristic directions on which this relation is satisfied. Okay. So, then making use of this, we compute the grid as an intersection of the characteristics, and at each grid point we have to calculate the solution. However, to calculate we need the grid points. Now, in order to get the grid points, we treat them as straight lines and compute the intersection point r. How do we do that? First, the characteristic lines have been linearized with the interpolation, and we get two relations using which one can obtain x r and t r. That means, we have obtained the point r. Once we get this point, we would like to get the derivatives, right. Solution u is obtained in terms of the first derivatives. So, now in order to get the first derivatives, we approximate, then we get these two equations. Now, the remark is, if x r and t r are known, then we get p r and q r from these two, from E 3 and E 4. Once we know these, our ultimate aim is to get the solution u at r. However, what we did, we have replaced here by average at P r and P p for a better approximation. So, unless we solve a problem, it is a little hard to follow, but however, it is a very beautiful concept. This has originated from the analytical treatment, because in analytical treatment we capture the solution based on characteristic curves. So, via discretizing the characteristic grid, we compute the solution and we march past. So, maybe we do some problems so that we understand this better. Thank you.